Okay, now we're going to start with our Chapter 14 practice problems. So Chapter 14 is actually one of my favorite. Chapter 14 and 15, students usually really like these, and they kind of stand alone in terms of they don't build as much as some of the other ones do. So I think you guys are going to like these. So for these practice problems, I'm going to go ahead and have you memorize phenol, anisole. That's a CH3 group. You should probably memorize annulen, toluene. Those are probably the main ones. Maybe also do benzoic acid. Benzoic acid. Acetophenone's also a good one. And this one comes up less often, but still worthwhile to know it. Benzene sulfonic acid. Benzene sulfonic acid. So if you memorize these 7 structures, I think your life is going to be a lot easier for the nomenclature. The other thing is for benzene. If you have only 2 substituents, this only works if you have 2 substituents, whatever the first substituent is, say there's one right here. Directly adjacent, that's known as ortho. 2 away is meta, and 3 away is para. So for me, I always just go ortho, meta, para. I just do it every time. I write OMP from your first one. It's a common name that we only use if benzene only has 2 substituents. So here's a perfect example, this first one. The correct name for the compound shown below, well, as a naming system generally, if it has one of these high priority names, that would be the basis. So phenol, that's going to be your first one. And then ortho, meta, and para. So the chlorine is ortho to the alcohol group that makes it a phenol. So you would call it ortho, that's what the little O is for, chlorophenol. So that's it. That's how you would name it. As long as you have these memorized and you know this, it makes the 2 substituents really easy. The ortho meta also, there's 2 ortho positions, 2 meta positions, and a para. There's only one, but this is only good with 2 namings, 2 substituents. So it wouldn't if you had this, you wouldn't say meta, or let's see, this is ortho, meta, para. You wouldn't say ortho chlorophenol or something. You only use it if there's only 2 substituents. So this wouldn't be one that you could use the ortho meta para naming system on. Okay, so for the next one, so we have NH2, so that's aniline. That's one of our basic ones. Amines not, so we can go ahead and get rid of those. So then you just need to know, is it ortho, meta, or para? And it's meta, so it's meta-bromoaniline is the right answer. Okay, anisole, we know that the OCH3 is anisole. Toluene has just a CH3 group, so it's not toluene, and it's not phenol because that's an OH group. So it has to be either ortho, meta, or para anisole. So ortho, meta, para. So it's para nitroanisole is the right answer. So if you just have these 2 tricks down, you should be good for your, I'm going to say starting right here. You should be good for all of those only 2 substituent naming systems. Okay, so for answer choice, or for question 4, let's see, our basic is actually going to be, we have 1 methyl group, so it's toluene. So benzene isn't right. I guess bromobenzene could maybe work, but it doesn't even say 3-methyl bromobenzene. It just says 3-bromobenzene, so that wouldn't work. It would have to say that there's a methyl on there. So then that makes us either methylbenzene or toluene, but toluene is one of our common things we learned, so we wouldn't call it methylbenzene, we'd call it toluene. And that's ortho. So ortho bromotoluene. So these are just kind of trying to trick you. They're not even a full name. It's just 3-bromobenzene. Don't even know what that would be. Because if you numbered it 1, 2, 3 and put the bromobenzene there, we could just start from anywhere. So it just doesn't really make sense. So D is definitely the right answer. Okay, here's where things get more complicated. You can't just use ortho, meta, para. You actually have to number. Then numbering starts with your main substituent. So nitrobenzoic acid. Benzoic acid is our main substituent. So this is our benzoic acid. So we need 1, 2, 3, 4, 5, 6. Start with your main substituent. Whatever gives it the name is number 1. 2 would be bromo. 3, 4, 5 is nitro. So we want to be able to number which one is not 2-bromo. So we need to be able to find these numbering system on all of them. So 1, 2, 3, 4, 5 on this one. Sorry, I covered up my hand. 1, 2, 3, 4, 5. So we've got benzoic acid 1, bromo 2, nitro 5. That is, so it's not the right answer. 1, 2, 3, 4, 5. So nitro 5, bromo 2, and benzoic acid 1. So that is this. So it's not the right answer because we're looking for whatever one is not that. 1, 2, 3, 4, 5. So that's right as well. 1, 2, 3, 4, 5, 6. So this is at least one of your right answers because this is not 2-bromo 5-nitrobenzoic acid. 1, 2, 3, 4, 5. This has everything in the right place. So your answer choice is D. So on these kinds of questions, always draw it and make sure you pay attention to what it's actually asking for, because when I first worked this problem, I was looking for which one was this. So it can kind of mix you up. The correct name for the compound shown below. So annulen is one of the things that we learned, one that we memorized from the first page. So that's obviously going to be number 1. Then you want to number these substituents towards the lowest it could be. So if this is 1, then you want that to be 2 because this would be 3. So a lower number is 2. So 2, 3, 4, 5. So 2, 5 dibromo annulen. So the right answer choice on that would be answer choice C. Okay. Okay, so your next question is going to be 4-amino 2-bromoanisole. So I'm going to just go ahead and draw it. Anisole, we learned, looks like this. This doesn't even have anisole. It has ACH2 and then the oxygen, so that's not right. This also doesn't, oh yeah, that does have, this doesn't have anisole because that's a ketone. That would be acetophenone. So that narrows it down. Just by knowing what anisole is, you've narrowed it down to 3 answer choices. So it is 4-amino 2-bromo. So that's 1, so 2, 3, 4. So 2 would be bromo, and 4 would be amino. So an amine is NH3. So these nitros can go, and that only leaves 1. So if you just knew the name of amino, bromo, and anisole, you could get it right without even knowing the numbering system. 1, 2, 3, 4. So answer choice D is correct. Which reagent would serve as the basis for a simple chemical test that would distinguish between benzene and hexene? Okay, benzene is an aromatic compound. It does not react the same way as double bonds do. It has special reactions that we'll learn all about in chapter 15. So anything that you know reacts with a double bond is not going to react the same way with benzene. NaOH, we haven't really even seen NaOH react with double bonds at all, so that's a silly answer. Br2 and CCl4, we did see it react with double bonds, so that's a good option because it would react with this, but it would not react with this. Silver nitrate, we haven't really learned about that at all, so that's probably not going to be it. Yeah, so I would go with answer choice B, because in sodium, what is that, sulfuric acid, sodium sulfate, would not go with, we don't know how any of those react with double bonds. You want something that definitely would react with a double bond and something that wouldn't. So almost a different way to ask this question would be, what's something that you know reacts with a double bond, but probably won't react with benzene because it's aromatic and we haven't learned reactions with benzene? And that would give you answer choice B. Okay, so for question 9, why would cyclohexadiene undergo dehydrogenation, not dehydration, dehydrogenation readily? Okay, 1,3-cyclohexadiene, if it underwent dehydrogenation, would become benzene. Benzene is extremely stable. It's an aromatic compound. We'll talk about that. I guess we could go ahead and talk about it now. Yeah, let's do that. Okay, if you have a ring, a conjugated system that becomes a ring, and its pi energy increases, that's anti-aromatic. If you have something that becomes a ring and its pi energy decreases, so it becomes more stable, that's aromatic. Aromatic compounds are extremely stable, and that's what makes them great, is they're so stable. Their pi energy is less than you would think it would be based on this ring. So if you have this and you put it into a ring, the energy goes up, it's less stable, it's anti-aromatic. If you have this and put it into a ring, its pi energy goes down and it becomes more stable, it's aromatic. So in this case, if you can go from this to this, the pi energy would go down, which means it would become much more stable. So the right answer is answer choice D. Okay, now how can we tell if something is aromatic, anti-aromatic, or non-aromatic? You look for 3 things. Does it have 4n plus 2 pi electrons? Is it a continuous ring with pi orbitals? And is it planar? 4n plus 2 pi electrons really confuses a lot of people. All that means is it a multiple of 4n plus 2? So if 4 times 0 plus 2 equals 2, if it has 2 pi electrons, that's good. If n is 1, 4 times 1 is 4, plus 2 is 6. If it has 6 pi electrons, we're good. If it has 10 pi electrons, we're good. If it has 14 pi electrons, we're good. So basically, if it is a derivative of 4n plus 2, if 4n plus 2 could give you that number by plugging in any number for n, then we're good. A continuous ring of pi molecular orbitals means that it has to be sp2 hybridized so that there's a p orbital all the way around. And then planar, most things, if they meet this and this, are planar. The exception is 10-annulene. 10-annulene is not an aromatic ring because it's not planar. It's just one of those things that you have to memorize. And that doesn't mean anything with 10 electrons, just 10-annulene. You can go check that out. I don't think we have a question on that. So this question is about cyclooctatetraene. So the easiest way for me to draw octane rings is like this. So cyclooctatetraene looks like this. So it has 2, 4, 6, 8 pi electrons. So it does not have 4n plus 2 pi electrons, but it does have a continuous ring of pi molecular orbitals around it. So if you have 4n pi electrons, then it's going to be anti-aromatic. So this is anti-aromatic. So the pi energy will increase. It's not as stable as benzene. So if we're going to go through all these statements with all that background information, I know it's kind of a lot. Will this compound rapidly decolorize bromine? So basically it's asking, bromine's like brown, does it react with bromine? It would react with bromine because it's not aromatic. So that's not our answer. Would it react with KMNO4? It would react with KMNO4 because it acts like a double bond, not like an aromatic ring, because it's not aromatic. readily adds hydrogen. I'm sure it does. It's not like a benzene. If you put a hydrogenation, like hydrogen with platinum or palladium, it would go through hydrogenation. This compound is non-planar. Yeah, if it was aromatic, it would be planar, but it's not, so it isn't. So this is the only one that's not true. This compound is not comparable to benzene in stability because it's very much less stable than benzene. It is unstable because it's anti-aromatic. So it's basically just asking you, do you know that cyclooctatetraene is anti-aromatic, and do you know that aromatic compounds are way less stable than benzene? Next question. Cyclopentadiene is unusually acidic for a hydrocarbon. An explanation for this is, okay, so they're talking about this hydrogen specifically. This reaction takes place very easily. An explanation for this is you have p orbitals all the way around, and there's 2, 4, 6 pi electrons. So that's 4n plus 2 pi electrons. It's not 10 annulene, so it's planar. So if you remove that proton, the cyclopentadiene anion becomes aromatic. So the carbon atoms of them are all sp2 hybridized. That's not true until you lose it, so that's not the right answer. Cyclopentadiene itself is not aromatic. It's non-aromatic because it doesn't have an sp3. It doesn't have sp2 all the way around. It doesn't have a pi orbital all the way around. It does not form a free radical to remove an anion. To remove a proton, it's usually going to form an anion, not a radical. And removal of the hydride ion makes a cation, but it would be an anti-aromatic cation. If you removed a hydride ion, that would mean removing the proton with its 2, which is not what an acid does, and it would make a cation that was anti-aromatic. So that's wrong all kinds of ways. So that's how you can work through question 11. Question 12 is basically just asking which cyclization would occur with a decrease in pi electron energy. So which of these is aromatic? So for all of these, we're looking for 4n plus 2 pi electrons, a continuous pi orbitals, and planar. 1, 2, and 3. So all these are continuous pi orbitals, continuous pi orbitals, continuous pi orbitals. So they all meet criterion 2. Now we're looking for 4n plus 2 pi electrons. This has, and try to quiz yourself. Do you know how many pi electrons it has? It has 4 pi electrons. So if it has 4 pi electrons, then it's going to be anti-aromatic. So that is an increase in pi electron energy. That's what anti-aromatic means. This has 2 pi electrons. 4n plus 2, where n is 0, gives you 2 pi electrons. So this should be aromatic. If it has these and this, it's usually going to be planar unless it's 10 annulene. This has 3 pi electrons, so it's not a derivative of 4n plus 2. And this has 4, so this is anti-aromatic. So the only one that should decrease in pi electrons should be the aromatic one, and that's answer choice B. Okay, for question 13, application of the polygon and circle technique reveals what? So first, let's talk about the polygon and circle technique. For the polygon and circle technique, you want to draw your, whatever the shape of your potentially aromatic compound is, with a point going downwards. You need to have one vertex pointing downwards, and then you're going to draw a circle around it. I'm terrible at drawing a circle around it. Anywhere a point meets, that's where a molecular orbital is. I think this is way easier than the other way of understanding molecular orbital diagrams, because all we're doing is drawing shapes. The biggest thing you have to make sure is that your point is downwards. You only have one by itself on the bottom. And then you've got your molecular orbital diagram. So I highly recommend you can do this. I mean, you're almost guaranteed to be tested on at least cyclopropane, cyclobutane. I left that one out. And for this one, people always forget to put the point down. So be sure cyclobutane does not It has to have a point down. This is not the proper molecular orbital for cyclobutane. You're probably going to be tested on at least cyclopropane, cyclobutane, cyclopentane, or benzene, so cyclohexane. So be able to draw all of these. It's going to come up on your exam. I can almost guarantee it. So this is asking, application of the polygon and circle technique reveals that single electrons occupy each of the two non-bonding orbitals in which? Cyclobutadiene, that's over here, it has 4 pi electrons. So 1, 2, 3, 4. So it actually does have a single electron in each of the non-bonding. Remember, we learned in the last chapter that non-bonding is if you draw a line right in the middle. For benzene, there's actually no non-bonding molecular orbitals, so that wouldn't be right. For cyclopropenyl cation, it only has 2 pi electrons, and I don't think it technically has a non-bonding orbital anyway, so that would not be right. Cyclopentadiene, again, I guess technically this would be the non-bonding line here. I don't know, actually, technically. I should probably go look this up if it falls between these two. But it wouldn't be right anyway, because if you have the anion, it has 6 pi electrons, so it would be like this. I think the non-bonding line is in the middle here. I think, but I can't be positive on that. I don't want to teach you wrong, so be sure you look that up before the exam. Don't take my word for it. And then the cyclopentadienyl anion, oh, that's the one we just did. Cycloheptatrienyl cation. So cycloheptatrienyl, that's 7. This is much harder to draw, but it'd be 7, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. Cycloheptatrienyl, I guess, would look something like this. 1, 2, 3, 4, 5. Is that right? 6. 1, 2, 3, 4, 5, 6, 7. That should be right. So 1, 2, 3, and then a cation. So that actually, I do this bond too long. Let me start over. That's terrible, but I cannot draw the heptane rings. Okay, let's see. 1, 2, 3, 4, 5, 6, 7. Oh, so it'd be a straight line across there. So you'd have 1, 2, 3, and then the cation right there. There you go. That's it. So these have 2, 4, 6 pi electrons. So actually this is aromatic. So none of these have 2 single occupying their non-bonding orbitals except for cyclobutadiene. Okay, applying of the polygon and circle technique, how many pi antibonding molecular orbitals are there? It doesn't say for what structure, so I'm just going to say for application of the polygon, how many pi antibonding molecular orbitals are there for benzene? So for benzene, you have your hexagon, 1, 2, 3, 4, 5, 6. If you draw a dotted line right here through the middle, you have 3 bonding, 3 antibonding, and 0 non-bonding, because it's the non-bonding line is right through the middle. So you've got 3 antibonding molecular orbitals for benzene. It doesn't say, and there's not an answer given actually, but I just pick benzene. You should be able to answer that for all of these. How many antibonding orbitals are there in cyclobutadiene? There's 1. In cyclopropenyl, 2. You should be able to answer those. Okay, in which of the following compounds would the shortest carbon-carbon bond be found? So this is actually way back into Gen Chem, but a single bond is longer than a double bond is longer than a triple bond. So shortest bonds are usually triple bonds. If you're in if you're in resonance like benzene, these actually fall somewhere between 1 and 2 because they're in resonance. So they're actually, all of them are the average of the 2 bond lengths. So, and the reason it's shorter is I think of it like if you have 1 bond, 2 bonder things getting closer, 3 bonder things getting even closer. Or like the buttons on a shirt. If you have 1 button done, these are kind of loosely held together. But if you have 2 points of contact, these are less loosely held together. And if you have 3 points of contact, it's very hard to draw to show this on this camera. It's going to be even more tightly held together. So the more points of contact you have, the closer together these two atoms will be held. So the only one that even has triple bonds is this one. So that's got to be your answer. Which of the following statements regarding the cyclopentadienyl cation is correct? So cyclopentadiene, penta is 5, diene, and it's a cation. So it's asking aromatic, anti-aromatic, whatever. It has 4 in electrons because it has 4 electrons. So it has pi orbitals all the way around. So that means it must be anti-aromatic. So it is not aromatic. It would be even more correct to say it's anti-aromatic. Doesn't obey Huckel's rule. It's not aromatic. We just proved that. Huckel's rule is the 4n plus 2 pi electrons. Undergoes reactions characteristic of benzene, not if it's anti-aromatic, and it has a closed shell of 6 pi electrons. It has 4 pi electrons. All these other statements would be true except B if it was the cyclopentadienyl anion. But because it's the cation, it's not true. Which of the following would you expect to be aromatic? Let's just go through all these and categorize them as anti-aromatic, aromatic, or non-aromatic. So 1, 2, 3, 4. 4 in pi electrons. It does have continuous rings around it. So this would be anti. This has a continuous ring of pi electrons. 1, 2, 3, 4 pi electrons. So 4 in, so it's anti. This has a continuous ring of pi electrons. 2, 4 pi electrons, so it's anti. This does not have a continuous ring of pi electrons. So there's a pi electron here, 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 but not here because this is sp3 hybridized. So there's not a p electron to become a pi molecular orbital, or there's not a p atomic orbital to become a pi molecular orbital, just like we talked about at the beginning of chapter 13. So because of that, I would classify this as non-aromatic. And then this, though, because of the carbocation, that is sp2 hybridized, so it does have a p orbital. So this would be 2, 4, 6. So it has 6 pi electrons, so that's 4n plus 2. It has an unbroken ring of pi orbitals. And it's not 10 annulene, so it must be aromatic. It must be planar. So answer choice E is your answer. Okay, for question 18, which of the following would you expect to show aromatic character? So this has an unbroken chain. This doesn't have an unbroken chain. It has an sp3. So it does not have an unbroken chain of p orbitals. So this is not going to be aromatic. That's non-aromatic. This does. All these are sp2 hybridized. All these are sp2 hybridized, and all these are sp2 hybridized. So all these have an unbroken chain. So all of those meet the unbroken chain of pi electrons. The next thing we want to look for, 4n plus 2 pi electrons. This has 2, 4, 6 pi electrons. This right here, even though it allows for the aromatic character, these pi electrons are not in the ring here. They're much more drawn to the oxygen. So this actually has 6 pi electrons. But it's just kind of weird. This has 2, 4, 6, 8 pi electrons. So this is anti-aromatic. So that's definitely not going to. And this is, I would say, non-aromatic because it has that radical. At the very least, it's non-aromatic. It might be anti-aromatic. So the only one that could be even close is going to be B. So that's just to show you that basically if you have a carbonyl carbon, it can lend a p orbital without adding any electrons. Okay. Now again, which one of these are going to be aromatic, anti-aromatic, or non? We've seen cyclobutadiene a lot. This has an unbroken ring of pi orbitals, and it has 4 in pi electrons, so this is anti-aromatic. Same thing here, we've got 1, 2, 3 p orbitals, and it has 4, so it's anti-aromatic. 1, 2, 3, 4 pi electrons. This is non-aromatic. It does not have an sp2 hybridized. It's sp3 hybridized right there, so it's not aromatic because it can't have the unbroken chain of pi electrons, or of pi orbitals. We've seen the cyclopentadienyl anion a few times, but just to go back over it again, you have 1, 2, 3, 4, 5 pi orbitals, so it's an unbroken chain. You have this lone pair, which makes it 2, 4, 6, and it's not 10 annulene, so it's planar. So this is aromatic. Here we have 2, 4, well, I guess all these has an unbroken chain of pi molecular orbitals all the way around. And we have 2, 4, 6, 8, so that's 4N, so this is anti-aromatic. So far, these are our anti-aromatics. Okay, and then here we have 2, 4, 6 of the electrons on an unbroken chain of pi orbitals. Now, this nitrogen is a little interesting. I guess we'll talk more about heteroatoms on the next question, but this does have 6 of the pi orbitals, so this would be aromatic. This has an unbroken ring of p, but it's 2, 4, 6, 8, 10, so that's aromatic. But it's not 10 annulene. 10 annulene is a 10-membered ring with alternating double bonds. I guess it would be with alternating double bonds, and that is not going to be, that's not planar. So that's the exception to aromaticity, but this is still aromatic. This is non-aromatic because it has an sp3 right here, and this is aromatic. So our right answer to which ones of these is anti-aromatic is 1, 3, and 5. So that's answer choice B. Okay, now let's talk about heteroatoms because they are a little weird when it comes to aromaticity. When we think of heteroatoms in aromatic, we want to think of the fact that aromatic compounds need to have all their p orbitals lined up facing the same direction. But p orbitals, if you remember from way back in Gen Chem, there's p orbitals in all of the axes. So there's up and down, side to side, and then going into and coming out of the page, right? So if you have, for example, a heteroatom with 2 p orbitals, so like an oxygen with a lone pair, you can have this lone pair going up and down, or you can have the lone pair going into the plane of the page, or you can have it in the x-axis. So you can have the p orbitals in 2 different, basically, axes of your molecule, but only 1 p orbital can be in the same plane as your ring. In addition, if it's not going to be in the aromatic ring, it would rather be hybridized. So you can think of your heteroatoms as having one, if they are able to, one of the lone pair that's hybridized and one lone pair that's in your ring of p orbitals, or one of their double bonds will be in the p orbitals and their lone pair will be hybridized. So let's look at that at question, or at option answer choice A as our first example. And also, aromatic rings want to exist. So if there's a way for something to be an aromatic ring, it's going to. That's just the tendency of molecules, is to be more stable. So let's look here. This nitrogen already has this double bond in a p orbital. So instead of keeping this lone pair also in a p orbital that's going to possibly mess up the aromaticity of this molecule, this lone pair is actually going to be probably hybridized in an sp2 hybridized orbital. Alternatively, it'll be in a p orbital, but it'll be a p orbital that's in a different axis as the rest of these p orbitals, so it's irrelevant to the aromatic ring. So that's going to be hybridized off in a way and not a relevant lone pair for our pi molecular orbitals that we're looking for. Same thing with this oxygen. one of these lone pairs will be in one pi orbital and one will be in another pi orbital, or more likely, it'll be hybridized into an sp2. So one will be part of an sp2 hybrid because that's lower energy, and the other will be in this unbroken ring of pi orbitals. It's not possible for that oxygen to have two in the same perpendicular pi orbital. So what that means, or have two lone pairs, so it can have 4 electrons. So what that means is you have 2 electrons here contributing to the pi orbital. These are not pi electrons, and neither are these. These are likely hybridized in an sp2 hybrid orbital. So you have 2, 4, 6. So this is aromatic. Okay, let's look here. Again, this is already part of the p chain. So because this double bond is taking up these p orbitals, this lone pair is likely not going to come into play. It's going to be hybridized in an sp2 hybridized orbital. So that's not one of your preferred lone pairs. That's not going to be part of your pi molecule or pi orbital. It's not a pi electron for your 4n plus 2 pi. Same thing here. You can have one of these lone pairs be in this chain, and the other one is going to be sp2 hybridized. So this molecule would have 2, 4, 6. So this would also be aromatic. This is not aromatic because it's missing this p orbital. But so this has 2, 4, okay, and this is a p orbital, but it doesn't have any electrons really in it contributing to the ring, just like we saw earlier. So then on our oxygen, only one of these can be in the p orbital, and the other one will be sp2 hybridized. So this would have 2, 4, 6 pi electrons. So this is aromatic. This is non-aromatic. And then this nitrogen, the pi bond can't move, so it takes priority. So these two are going to be in the p orbital. This is likely to be sp2 hybridized. And then here, there's not a double bond on this, so this one lone pair will be in a p orbital. So we always learned in Gen Chem, if you have this is sp3 hybridized always, but it's not always sp3 hybridized. It will likely be sp2 hybridized and have the lone pair in a p orbital if it can go into aromaticity, because that's lower energy. If aromaticity is not an option, then it'll be sp3 hybridized because that's lower energy. So the molecule is going to do whatever it can do to get lower energy. So kind of when they told you that this was sp3 hybridized, they lied a little bit. It's sp3 hybridized if there's not a better option for lower energy like there is here. So this is actually probably an sp2 hybridized nitrogen with this lone pair in its own p orbital. So that's how I think about heteroatoms in aromaticity. Okay, so which of the following would you expect to be anti-aromatic? Well, we've seen cyclobutadiene a lot, so that one's going to be anti-aromatic. We know benzene's aromatic, so that's not going to be aromatic. Let's see, 2, 4, 6, unbroken chain of pi electrons. 6 is 4n plus 2 pi. So, hang on just a second. Sorry about that, my phone went off. Okay, so back to this, we've got 6 pi electrons, which means it's 4n plus 2 pi. 2, 4, 6. This is an empty p orbital, so it doesn't contribute pi electrons. We have the unbroken chain, and it's not 10 annulene, so it's planar. So that's not going to be anti-aromatic. This has 2 pi electrons, so that's 4n plus 2 pi. It's an unbroken chain, and it's not 10 annulene, so it's planar. So that's not going to be. And 2, 4, 6, that's also not going to be. It's got 6 pi electrons, unbroken chain. So you knew right away, based on all of the looking, that cyclobutadiene is going to be anti-aromatic. We've done that a lot already on this practice problem, but you still want to check because sometimes multiple things could be the right answer. Okay, which of these would you expect to have significant resonance stabilization energy? So that's another way of asking which of these is going to be aromatic. So I would expect this lone pair to be hybridized because there's already a p orbital here. I would expect this one of these lone pairs to be hybridized. So 2, 4, 6. So I would expect this to be aromatic. Answer choice 1. For answer choice 2, I would expect this to be sp2 hybridized because there's already a p orbital for these double bonds. And then it's basically the same structure as 1, only with a sulfur instead of oxygen. I think this would be sp2. So we have 2, 4, 6. So this would also be aromatic. Oh, all these are very close to the same molecule. The nitrogen has just moved. So these are very similar. So this is sp2. So you've got a lone pair here that's hybridized, and then a lone pair here that's hybridized. So 2, 4, 6. So I'd expect all of these to be aromatic. So really this chapter is so much about aromaticity. So if you can name aromatic compounds and identify aromatic compounds, you're in good shape for this exam. I mean, there's more subtlety to it, but that's a lot of what this chapter is. So I think students usually have a better grasp on that. Okay, which of these species is aromatic? So I would say this one's non-aromatic because it has an sp3 hybridized right there. This one's non-aromatic because it has 2 sp3 hybridized, and this one's non-aromatic because it has 2 sp3 hybridized. So always check for the unbroken chain of sp2s. Then look for 4n plus 2 pi electrons. So let's look for that. 2, 4, one of these will be in, and the other one will be hybridized. So 2, 4, 6, and this is an unbroken chain. It just doesn't contribute. So this would be aromatic. This would have 1 in the sp2. Now this one's interesting. It's not going to be aromatic. It could be anti-aromatic, but I expect it to be non-aromatic because one of these could go into a p orbital, and then this could be sp2. But then you'd have 2, 4, 6, 8, and that would make it anti-aromatic. The other option, and I think this is what would happen, is this oxygen could be sp3 hybridized, which means it wouldn't have an unbroken chain, so it would be non-aromatic. I think that would be more stable, and so I think that would happen, is one of these oxygens would stay in an sp3 hybridized state. I don't know for sure, and we'd probably have to look up the right answer to that, but it's definitely not aromatic, so it's not going to be your answer. So answer choice B is your right answer. Okay, now let's talk about annulenes. Annulenes are kind of hard for me to draw, but this benzene is also known as 6-annulene. So it's the number of pi electrons in a structure that's a ring with alternating double bonds. So this is 8-annulene. This is 6-annulene. This is 8-annulene. 10-annulene, I told you guys about that one already. Let's see how many is this? 1, 2, 3, 4. 1, 2, 3, 4, 5. So this is 10-annulene. 10-annulene has 4n plus 2 pi electrons, but it's non-planar. So what's convenient about these annulenes is it has a number of pi electrons in brackets, and then annulene means ring with alternating double bonds, basically. So what you're looking for is 4n plus 2 pi electrons. So luckily they don't have 10-annulene on there for you because it's an exception. But 6 is 4n plus 2 pi, where n equals 1. 14 is 4n plus 2 pi, where n equals 3, because 4 times 3 is 12, plus 2 is 14. 16 is 4 times 4, so that's 4n, so I would expect that to be anti-aromatic. 18 is 4n plus 2, where n equals 4. And 22, what's that? 4 times 5 is 20. So 4n plus 2, for N equals 5. So that means the only one that could be anti-aromatic would be 16-annuline. So that's an overview of chapter 14. I hope that was helpful for you guys. If you have any questions, please feel free to reach out to me.